Let's try to find an equation that describes space, time, position, and direction. Probably the most fundamental ideas in physics. I mean, this is called classic physics to its at its finest. Probably the easiest way to use to find that would be to realize that the pull of gravity on Earth is fairly well consistent. So we can say the acceleration on Earth is going to be a negative g. Our g is usually is 32.2 feet per second squared, or 9.8 feet per second squared. In this case, it doesn't matter. We're just going to find the equation, a generalized equation for this. Anyway, this is going to be in the j direction because x is going to be in the I direction, y would be in the j direction, and of course z would be in the k direction. So let's look at acceleration first. Nice way to find out how things are going on is find out position, direction, space, and time. So if we take the integral of this thing, we're going to find the velocity. All right, so let's see, velocity in time. We're going to take the time integral of this thing, so we can pull the g out. Doesn't really matter. There are no boundaries, so this is dt. Nice simple integral, probably the easiest integral you're ever going to get. So our velocity t is going to end up looking like this. Negative gt in the j direction plus c1. All right, well, there's a very rudimentary equation of what velocity would look like. We have time, we have space, but we don't have anything with direction. All right, so let's take the integral of this thing, and we'll get our position. So r of t is going to be equal to the integral. We can pull that g out again. The integral of t dt plus, you can pull it since it's a constant, we can pull this out, constant 1, integral dt. Again, two very simple integrals, nothing difficult here at all. R of t is going to end up equaling 1/2 gt squared in the j direction plus c1 times t plus c2. Since there's no boundaries in this integral, we got to add another constant. So this is a very rudimentary equation of space, time, but no direction yet. We don't know what directions c1 and c2 are. In fact, they're just both of them are just vectors. Okay, so let's think about what c1 could be. Well, c1 is right here. If we take velocity initial, where time is 0, this t becomes 0, so that velocity t ends up being c1. Okay, let's look at that. So r of t is going to equal to negative 1/2 g t squared in the j direction plus, we know what c1 is, it's actually the velocity initial, t times t plus c2, right? Well, c2 is right here, right? We can also do the same thing as well. Position initial is going to mean that time is 0, so this is 0, this is 0, so this actually becomes r initial t. So this is even a better equation, even a closer equation than what this is. But the only problem that we have here is that we still don't have any directions. We don't know what direction this is. We don't know what direction this is. Okay, we also have this in j direction. We got to keep our eye, make sure realize this isn't the I direction. This is velocity initial. This is position initial. Well, let's look at that. Let's think about how we can find the direction of these things. Plus the directions of c1 and c2. How are we going to find those? Probably the easiest way to find these directions is to realize that in the x and y world, we're only using 2 dimensions right now. So this is going to be our x direction. This will be our y direction. If we have some sort of parabolic motion, it's going to look similar to this on Earth. So here we are at Earth. It's going to look similar to that. If it's at a particular height, This would be our particular height at which the thing is thrown. Or it could be a football, it could be a baseball, it could be whatever the case may be. It's always going to take this paralobic kind of motion, because in gravity has geometry associated with it. So it's going to have this paralobic motion. One thing we have to understand is that when you first or initially throw the thing, you're going to have a velocity initial, right? You're going to have this thing right here. You're going to have some sort of velocity initial. Well, let's give it some direction. The easiest way to give it direction, well, let's find out what angle it's being thrown at. So whatever angle it's being thrown at, could be this angle, could be this angle, could be this angle, could be straight up, whatever the case may be. So this is going to give us a direction. Well, that's easy enough. Well, then what is going to be our velocity in the y direction? Well, let's see. Opposite over hypotenuse is going to be our sine, right? So we're going to say velocity initial sine theta is going to be our y direction, all right? Or j, whatever you want to say it. It's probably easier if we use j, because then we won't think there's down here. So then we know this. We know our y velocity. Let's find our x velocity. Well, that would be what? Cosine would be what? Adjacent over hypotenuse. So my velocity initial is going to be equal to the cosine, velocity initial times the cosine is going to be equal to x direction, or I. Great. Well, then, vectorially speaking, when we add this up vectorially, because that's what we want to find is velocity initial, that's going to be what? Velocity initial times the cosine theta in the I direction plus velocity initial times the sine of theta in the j direction. Oh, well, there you go. This would give us direction. We can actually put this down into here and find our direction. Let's do that. Okay, why not? Let's see what happens when we do that. So if we put that in there, we're going to have r sub t is going to be equal to our negative 1/2 gt squared in the j direction. Velocity initial now, this is going to be plus this thing. Velocity initial cosine theta I plus velocity initial sine theta j times t, right? Plus, well, what's our r of t? Well, that's going to be how high it is. This is going to be the position vector, right? How high is the thing up in the air, right? We don't look at it as, we want to look at this as being the origin and this being how high it is in the air. So this would be basically r of t is going to be equal to h. So we can say plus h. And what direction is that? That's going to be a what? In the j direction. All right, so we're almost home. We are almost home. The next thing we got to do is we have a j, we have i's, we have another j, we have another j. Let's put our i's and j's together. And then we'll factor in this t. So r of t is going to end up looking like negative 1/2 gt squared. Let's find out. Let's go I direction first. Let's go with velocity initial cosine theta times t in the I direction plus, let's put this in parentheses or in brackets rather, plus h plus what? Velocity initial sine theta times t, and then minus 1/2 gt squared, and all of this is in the j direction. There you go. We have found an equation. We found an equation that relates position, direction, time, and space. So this is going to be our position. Where is it? This is going to be our direction. What direction is it going? This is going to be our time. And of course, velocity happens in space. Gravity happens in space. So you have all four of those are all connected with this one equation. This equation will tell you no matter what situation in you have, as long as you know velocity initial and your angle, you will be able to tell exactly where something is in time, space, and direction. In other words, if you throw a football, all you need to know is the angle that it's thrown at and the velocity initial, and you'll know pretty much everything about where that football is going to go. This is such classic physics. You cannot use this with an electron. It will not work. You cannot use this with a photon. It will not work. But in classic physics, as far as the macro world is concerned, this thing will tell you exactly where something will be. Pretty close. Not exactly, not absolutely exactly, but pretty darn close. All right, so let's look at this thing right here. This thing right here has time in it, it has direction, it also has space. If we solve this thing for t, right, we're going to find out how long an object remains in the air. In other words, if we solve this for t, we'll find out how long the object is in the air. So how do we solve this thing for t? Well, look at this thing. This is going to be, if we just move it around a little bit, this will be -1/2 g t squared, right, plus velocity initial sine theta times t, right, plus h. All right, well, that looks an awful lot like ax squared plus bx plus c equals 0, right? Doesn't that look very similar? Of course it does. Well, that means we can use what? The quadratic equation to solve this thing? We certainly can. What's the quadratic equation? What? -b plus or minus b squared minus 4ac square root of that thing divided by 2a. I hope that's it from my memory. All right, so let's apply that to this thing and see what we get. So b squared, let's look at this thing. So our time is going to be equal to b squared, which is what? Velocity initial. So this would be velocity initial sine theta, right? We don't bring along the t because we're solving for t. And this would be negative, and this could be negative, and this will be plus or minus, right? Our b squared, which would be velocity initial squared sine squared theta, what, minus 4 times a, which is -1/2 g, right? And then plus c, which is h. And then we take the square root of that thing, right? And then we divide the whole thing by 2a. So this would be 2 times -1/2 g. Okay? Well, that makes sense so far, right? We've found it in this particular manner. So let's keep on going. Let's see what we got next. Well, let's see. The negatives can cancel, so this all goes away. The negatives can cancel. This 2 cancels. We're going to end up with what? T is going to equal to velocity initial sine theta plus velocity squared sine squared. All right, so this is negative. This goes away. This ends up being a 2. The negatives go away, so it's be plus 2gh square root, right, divided by what? G. There you go. That is the amount of time the object will remain in the air. Hey, that's great. It really is velocity initial. That's great. This tells us the time object remains in the air. If you're talking about gravity. If you're talking about gravity, though. Great, fantastic. I wonder if we could put that anywhere else. Well, I'm sure we could. Let's see what's happening here. If this is our time, why can't we put this time into here? Well, we can. You actually can do that. Well, kind of running out of room, but I can do that. Let's see if I can do that with the amount of room I have. I need a bigger board. Maybe if I get more followers, I can get a bigger board. All right, so if I do that thing, I'm going to have cosine theta, right, times this thing, because velocity initial, cosine theta times this thing. So all of this has got to get in there. Velocity initial sine theta plus velocity initial squared sine squared theta plus 2gh. Take the square root of this thing divided by g, right? Hey, but we've done that. We put our t in here for that. What's this going to show us? This is going to show us how far downrange the thing goes, right? Because you're talking about the I direction now. So this is going to show us how far down range this thing will go. Since we're talking about this as being in the I direction, we're solving this thing right here. So this is going to be the I direction. So it's going to be how far down range does it go? How far down field does the football be thrown? How far down field has the baseball been thrown? Whatever the case may be. All right, so let's keep on going. Here we have a velocity initial squared. Let's pull that out, and we can pull this velocity out, initial squared. Because I want you to think about, because of 2 squared x square root, right? If we take that, that's going to be equal to what? Just 2x, 2 squared x? I mean x square root rather. So we can pull that out. So basically this is a 4. You can pull that 2 out. So you can do the same thing here. So we're going to have velocity initial cosine theta times velocity initial sine theta. So we're going to pull that velocity, or that, yeah, that we're going to pull that velocity squared out. So we're going to have plus velocity initial, right? So now when you pull that out, you have to be careful when you pull that out. So you're going to get sine squared theta plus 2 times g times h divided by velocity initial squared. And we're just going to put this as times, and we're going to put a g over here just to get rid of it. It's kind of in the way. And we can do one more thing. We can pull out a velocity initial here, can't we? Sure we can. If we pull out a velocity initial here, that makes that squared. So our range, how far down range it goes, is going to be, since we're pulling our velocities out, we're going to have velocity initial squared cosine theta divided by g, right, times sine theta plus the square root of sine squared theta plus 2gh divided by velocity initial squared square root. This will give us our range. This tells us how far downfield, or the maximum distance something will travel if we use this equation. This equation is very powerful. This equation is something that your physics teacher should probably teach you. One of the first things they should teach you, because it brings everything together. It brings in position, it brings in distance, it brings in direction, it brings in space, it brings in time. It kind of all ties it together, and it really does actually work. I'm pretty certain that the kickers and whatever else in the NFL are going to be using similar equations to this to find out how far down field it goes. That's why time is so important in how long the hang time is. It's so important so they find out where it's going to end and where it's going to land. All right, I hope this helps. On my next video, I'll use this. I'll show you exactly how this works. Appreciate it. Thank you. And I hope you subscribe.